Well, it's my turn to thank the organizers for inviting me here. It's a great pleasure to be here. This is my second time in India, and it's great, really. Thank you very much. So, more on big groups or small breadth. This is clearly a, what do you call it, a sequel, like big groups of small breadth strike back or something like that. It means simply that there is another paper that I'm referring to, some old paper, and it will come in my talk. Also, this is joint work with some friends of mine. I've been working with Norberto Gavioli for a long time now, about 20 years. And Andrea Cupaiolo is a PhD student of ours. And Alessandro Morresi Zuccari is a former postdoc of ours. You see a double affiliation there. And what I'm going to tell you is the fruit of some meetings we had at the Istituto Nazionale di Alta Matematica in Rome. And this is a nice occasion to thank them for their hospitality. We have a seminar there, a Friday evening seminar, and it's very nice to chat there at this place. So let's go to mathematics now. So this is the summary, the table of contents. Really, my talk is very easy and will include two parts. In the first one, I will give some definitions, something very easy, something that you have already seen even in other talks in this sequence, in this series. And I will explain how they interplay between these definitions. And the idea is that to create a set of tools to say something more on that paper that I will tell you about. So once we have these tools, we can somehow add something to the results of that paper, make them more detailed, more precise. And the second part will be exactly this. So we'll be going again into that paper and seeing how we can improve those results. Now, the first definition that I want to give is the definition of breadth. It's very well known, of course. From what people said here, I realized that what I'm going to say in the first part of the talk is something that everybody knows, probably. But for the sake of completeness, I want to say that again. Now, the first sentence tells you that I'm going to think about P groups, and mainly P groups of odd order, although this is not needed here. Of course, the definition of breadth and all the definitions that will come later can be given in a much wider generality. But, I mean, this is a talk, it's not a paper. So for clarity, I will take the fact that G is a finite P group as a sort of blanket assumption. I mean, in spite of the fact that you can generalize. So the breadth of an element is simply the logarithm of the length of its conjugacy class. And the breadth of the group will be simply the maximum of this, of the breadth of its element. Also, some notation that's very usual. The number of conjugacy classes of G will be indicated by K of G, and I will indicate by Ki of G the number of conjugacy classes of length P to the I. So the second definition that I give is the one of isoclinism. This was given by Primož yesterday in a slightly different context. But so if you have two groups, G and H, you say that there is an isoclinism between them if there are two isomorphisms, alpha and beta, the first going from the going between the two central factors of G and H, and the second between their commutator subgroups, in such a way that that diagram commutes. I would think of an isoclinism as a sort of saying that the two groups have the same commutation structure. This is an equivalence relation among groups. And this concept of stem group has been spoken about by Primož as well. These are the groups of smallest order in an isoclinism class, and they are characterized by the fact that the center is contained in the commutator subgroup. All this is in a very nice paper of Philip Hall in 1940. The central products, this is another very easy concept. It's a generalization of the direct product of groups. If you take, say, two groups, two are enough for me today, so far, I mean, to define. And, well, you can define the central product in two ways, like the direct product, a sort of internal way and external way. If you have two subgroups that centralize each other and the group is generated by them, you speak about the central product. Or equivalently, in a different way, you can take two groups and take their direct product and factor out a sort of identification of two central subgroups. Okay, so you need an isomorphism between two subgroups of the centers of them, and then you take that factor. This is a typical construction in groups, and the typical example, one typical example, is the extra special P groups. These are the groups whose center, commutator subgroup, and Frattini subgroup coincide in a group of order P. And these are central product of non-abelian P groups of order P cubed. I will use this later. Oh, nice. So let's see, if we take an element in a coset of the center of a P group, and we take another element in the same coset, clearly the centralizer, the set of commutators that this element forms with the other elements of G, and the breadth of G don't change. You're modifying just by an element in the center. And so this, we can define the breadth, the common breadth of the elements of a coset of the center of G as this is just the breadth of G. All have the same breadth as G. Observe that this is not the breadth of the coset as an element in the factor group. This is just the common breadth of the elements. Now, if I have an isoclinism between two groups, then clearly then if I take an element of a coset of the center and I take the map alpha that sends it to a coset of the center of H, then alpha sends the centralizer of that element modulo the center in the other centralizer, and the commutators, the set of the commutators. In this talk, the symbol square brackets little g, capital G will be the set of the commutators of G, of the element little g, E, and G. And also the breadth are the same. So the two elements, D and H, have the same breadth. The breadth is an isoclinic invariant. Well, then if you take the number of conjugacy classes that have breadth I, and you multiply this number by the common breadth of this element, or the common size of this, common length of these classes, well, you get all the elements of that breadth, the set of all the elements of that breadth. If you take that number, since the center is contained in that, since they are divided into cosets of the center, you can write that number in the way you say there, you see there. So you get here the number of cosets of the center of elements of breadth I. If you divide by the order of G and by P to the I, you get this expression. Observe that on the right-hand side, you have only isoclinic invariants. And therefore, this is an isoclinic invariant. And therefore, this, the commutativity of G, of which Primož spoke yesterday, is an isoclinic invariant. All this in Philip Hall's paper. There is nothing new so far, really. Now, I won't speak about the commutativity. I am within P groups now. A lot has been done about this in other contexts. I just want to tell you why, I mean, something that Primož said yesterday, the commutativity is really to be interpreted as the probability of two elements of a group to commute. You have to use the so-called, what Peter Neumann calls the lemma which is not Burnside's, the famous lemma that counts the orbits of an action. In this case, where the action is conjugacy, the number of conjugacy classes, the orbit, is just the average of the size of the centralizer, the fixed points, and of the size of the centralizers. And so this is simply, the sum of the sizes of the centralizer is simply the number of pairs that commute. And therefore, the commutativity is really the probability that picking up two elements of the group, they commute, as it's written there. Now that I have these numbers, I can use them, this ki of G divided by the order of G, I can use them as coefficients for a polynomial. And that's what I am doing here. This polynomial has, I mean, some values of this polynomial are significant. If you compute that at 1, you get the commutativity, of course. If you compute that at 0, you get the order of the center divided by the order of G. And if you compute that at P, you get just 1, of course. But this is all easy. Now, we want to construct something. We want to make some constructions with this idea, with these very simple definitions. Take a minimal normal subgroup of G, a normal subgroup of order P, and take an element of G. Now, the conjugacy class of X will collapse if, going to the factor group, it reduces its size. It means that the conjugacy class of X consists of cosets of N. Some of the conjugacy classes will collapse when you go to the factor group modulo N, and some will remain invariant, will keep their size. It means that they consist of one element in the conjugacy classes of Z of X, in the cosets of Z of X that contain some conjugate of X. So this is my notation for the number of invariant conjugacy classes of breadth I, Ki plus, and Ki minus will be the number of the collapsing G conjugacy classes. Okay. Now I write here clearly And by this I mean that this is what I write is plausible and easy to prove. And the proof is straightforward from the definitions. Not at all that it's trivial. It's just easy. So if you want to compute the number of conjugacy classes of breadth I of G bar, the factor group, well, you have to divide by P the number of invariant conjugacy classes, because P of them will make one conjugacy class of the factor group. And you have just to take the number of collapsing conjugacy classes. And if you divide by order of G, you get that expression. Adding up over I, those expressions, well, on the left you get the commutativity of G bar, and expressed in terms of the commutativity of G and of the number of invariant and invariant conjugacy classes of G. Now, this expression looks a bit like, let's go to the next one, the one possible expression of a famous formula by Burnside. You find this formula in Burnside's book. In the end, it is note E. This formula, which is in the book, is in this form, gives you the number of the conjugacy classes of G in terms of the conjugacy classes of a maximal subgroup and the number of the number S. Oh, sorry, no, sorry, the number S of invariant class G invariant M classes of M. Now, if you I mean fiddle around a little with this formula, you get this, which really look at this coefficients p squared 1 minus p squared, really looks like this one. So with some variations, of course. So you can think of what I wrote in this slide as a sort of dual of the Burnside formula. Okay. So let's now write more polynomials. Now, n was our minimal normal subgroup of G, and I define the collapsing and the invariant class-counting polynomials as before. Now I take these numbers. Now the collapsing class-counting polynomial will be just the sum of these coefficients, ki minus over the order of G. This will be the coefficients of the polynomial. Observe that it doesn't matter if I start summing from 0 or from 1, because of course the central classes do not collapse, cannot reduce their order. And similarly, I define the invariant class counting polynomial here. And again, since their coefficients are isoclinic invariants, the polynomial are invariant under isoclinism. Now, the idea is that now I can use these polynomials to compute. I mean, they have some nice features. If you take the class invariant polynomial of if you want the class invariant polynomial of the factor group G mod n, you just have to add the invariant class counting polynomial of G the invariant class counting polynomial, and P over X, the collapsing class counting polynomial. Now, the division by X doesn't spoil it, because we have seen that the collapsing class counting polynomial has 0 coefficients of degree 0. So you can divide by X. And also, if you have a direct product, you can simply multiply the class counting polynomial of the factor, polynomials of the factor, to get the class counting polynomial of the product. Together, this gives you a formula for a central product. You first take the direct product of the two groups and then factor out some subgroup of order P, and you get so algebraically you get the invariance, the isoclinic invariance for the central product just out of the isoclinic invariance of the two factors. Now, the sentence which is below needs some comment. In some sense, this allows us to focus on Stampy groups. If we want to compute those polynomials, those invariants, we can just look at Stampy groups, because we are within an isoclinism class, that do not have any proper central factor. Of course, in principle, if you repeat this construction several times, computations become very difficult, of course. But anyway, it makes sense to concentrate on computing this isoclinic invariance for the groups that are Stampy groups with no proper central factors. And now this is time to tell you something about the paper of which this is a sequel. This is a paper that was published in 1998. Well, Gavioli and I were there, and Valerio Monti, Avino Amman, and Andrea Previdali were the other co-authors. And we could find bounds for, in that paper we found bounds for P groups of small breadth for the number of conjugacy classes, for K of G. We have this, we gave these bounds. And a lower bound is the one which is in the box there. Look, this bound somehow is, well, of course, it's interesting, but the bound depends on the order of G. So if I'm thinking in terms of isoclinism, I don't like this part of the bound too much, because it depends on the order of G. I would like to have bounds. I would like to exhibit bounds today that are bounds for all the groups in the isoclinism class. So anyway, of course, you can take 1 over P to the B as a bound, and that's rougher, but anyway, it works. So this is for the lower bounds. And for the upper bounds, well, this is easy to find an upper bound because, well, you can use character theory. If you take the order of G, which is the sum of the squares of the irreducible character degrees, and so you take the linear characters on one side, and then you take the other characters that have at least the degree P, so their contribution to the sum will be at least K to the G minus order of G divided by the order of G prime P squared. And so out of that, you easily get this bound for the commutativity of G, the bound in the left, and observe that in the first inequality up there, right here, this the bound is actually, you can reach equality there if all the characters of the group that are non-linear have degree P, so that this inequality can be an equality really in that case. And now the next inequality is obtained simply by thinking that the order of the commutator subgroup is certainly bound above the order of every class, every conjugacy class of G, so the breadth. So groups whose character degrees are 1 and P, and these were studied. These are on Isaac's book. I mean, classical result. These groups are exactly those that either have a maximal abelian subgroup of index P, of course. This shouldn't be there. Of index P shouldn't be there. We are speaking about P groups, of course. But anyway, this is a small cut and paste mistake that I made. Okay, and or the center has very small index. Now, in the first case, we observe that we didn't observe. Philip Hall observed that already in his paper, that is in his 1940 paper, that the breadth outside the abelian, the maximal abelian normal subgroup, have all the same breadth B, and that the commutator subgroup has order P to the B. So the elements outside really cover the commutator subgroup with their commutators. And in this case, you get that the group has exactly this, this commutativity, which is nice. So the upper bound can be obtained. So let's put together the results. We have that the commutativity is bounded below by 1 over P to the B and above by 1 over P squared plus 1 over P to the B minus 1 over P to the B plus 2. Now, the bound below is strict, and the bound above, as we have just seen, can be an equality. And what happens, and what Alex was noticing yesterday, is that there are holes in this interval. Not every element of this, not every number within these two bounds can be K of G modulo the order of G, can be the commutativity. The commutativity is create a sort of spectrum within this interval. And so we proved 20 years ago that, 18 years ago, that there were these holes. And so where are the holes really? Can we use the simple constructions that we made before, that we worked out before, to pinpoint the values of the commutativity more exactly? Yeah, of course, we just commuted exactly the commutativity of a stem of any P group that has an abelian maximal subgroup. And can we compute the commutativity exactly of the class counting polynomials as well? I will speak about the commutativity for the sake of clarity, but of course you can compute all the coefficients of the polynomials, of course. For stem P groups without proper central factors, in order to use our techniques to compute the values of the same invariance for every P group. Now, I think that this is still far from a possibility to do computations with a machine. I mean, to implement an algorithm to do that. We have still lots of things to do before we can reach this goal, but the idea would be to produce an algorithm to compute the commutativity. And okay, this is nice. Okay, so I'm going through briefly through groups of small breadth, which are the topic of our old paper, and I will refine those results in the light of what I said so far. So P groups of breadth 1 were studied long time ago by Hans Knoche. So now we are assuming that we are speaking about a stem group. And in this case, we see that G is exaspecial. Its commutator subgroup is order P. Its center is the commutator subgroup. And so it's easy to compute its commutativity. I will, as I said already, I will bound myself to commutativity, not to the polynomials and all the coefficients of the polynomials. Sorry? Minimum value of M is 1, right? Right. This is an example of a group that has M equals 1 is the Heisenberg group for the field of order P, of course. We obtain that bound. Look, that bound somehow contains, we obtain that value, not the bound, contains the order of the group, because the n is 2m plus 1, but m is also the number of factors, of central factors, so I'm perfectly happy with this. This is, in some sense, very easy, but this is the ideal situation. We can compute the value of the two stem groups over the P cubed, and then out of that we compute all the values. That's easy, very easy. So if you go to 2, well, this is, they were characterized in our paper, really, and a year later by Gemma Parmigiani and then Bernd Stellmacher, in a totally independent way. They didn't use character theory in their characterization. And they were even more detailed in defining the classes. In giving details about characterizations. So basically, there are two possibilities. Either the index of the center of G is very small, or the order of G prime is very small. That's still very, very, very simple to treat. Reasonably simple to treat. So, I want to... Now, you have seen this slide. It's not a mistake that it reappears. I'm using the same results that I was using before to construct something different. Here, we know that we are, so we want to take the first case first. And so now the center is order P cubed. Now the same topic that I mentioned, the same theorem that I mentioned before on Isaac's book, gives us that the character degrees are just 1 and P. And then, as we did before, we get exactly this bound. Oops, sorry. This is a big distraction. You get really this number for the commutativity of G in this case, just the precise value of the commutativity. And it's important that we can show that G does not have any elements of breadth 1. I won't show this, but yes. So now take the other case. Now the commutator subgroup is order P squared in the other case. And we can deal dividing this in two cases. The first case is when G has class 2. Here we find something which is not something that we want. Yeah, I have just the time to do that. Because, you see, if G has class 2, we can only give, again, bounds. And one of these, this is the upper bound, which is fine, but this contains the order of G. this is something we cannot eliminate. There is a case, the case of, they are called either semi-extra special P groups or P groups of Kamina type. Basically, if I have a P group G, and I know that for every x in G minus the commutator subgroup, then the set of the commutators of x is the whole commutator subgroup. I have a group of this type. They were studied in 1976, I think, by Bert Weissenberg. And then later by Alan Kamina, that's why they are called Kamina groups, and by many other people, Ian MacDonald and many other people. And their structure, I mean, they're special groups, so they should be well known. They are well known. You can compute in them. You can easily compute, of course, in this condition, the coefficients of the class invariant polynomial, of the class counting polynomial, because the elements are either central. It turns out that G prime is also the center of this group. So either central elements or elements of breadth 2. You can just compute explicitly, but we don't have a clear understanding of how they can be decomposed in as central products. While for the groups of class 1, the extra special P groups are easily decomposable in a central product. Here, there is still this difficulty. So, although we can write explicitly the commutativity of semi-extra special P groups, as I call them, we cannot write it in terms of explicitly in terms of commutativity of central factors free groups of that type. Okay, so I have here just an expression of how a typical value in this interval would look like, but this is not, I mean, this is just there. And the other case is much easier somehow. It gives a much better result, because if the group has class 3, you don't have any problems. You can just compute 2 explicit values for the groups of class 3 of breadth 2 that are stem and do not contain any proper central factors. Just 2 numbers. That's it. And then out of those numbers, you construct the others. I should note here that we have a way I mean, we have an easy theorem that tells us that the order of a group of a P group that has a bounded index of the center is bounded. You can either use the only result of 1974 that I indicated there, or simply think that if the index of the center is bounded and the group is a stem group, then, well, of course, the commutator subgroup has bounded index, and therefore there is a bounded number of generators of bounded exponent, and therefore with an easy, the class is bounded because the index of the center is bounded, and therefore with an easy exercise in combinatorial group theory, you get a much worse bound on that group. You can even do it easily without using von Lee's theorem, but you don't get that nice bound. So if the order of the group is bounded, then there are only finitely many values for the commutativity, and so this is the ideal situation for us. Okay. And the last, that's fine, the last slide tells us something about breadth 3. I didn't put down a list of values for the commutativity because this is longer, of course. Things become more difficult here. Let me just say one short thing for each of the 3 cases. If you see that if the group has breadth 3, there are 3 possible cases. Let's start with case 3. If there is a factor group in which the center has very small index, this is the first possibility, then we can reach just the values of, we could compute just the values of the commutativity. The case 2, really, I found out here that needs a revision, because here I found out of a very nice paper of Manoj Kumar and Tushar Naik, right? That deals with groups in which the breadth of the elements are either 0, so central elements, or p to the 3rd power. And this accounts for part of result number 2. I'm very glad to mention it here, and this will be quoted in the final version of this paper. And for case 1, we have the same difficulty that we had before. I mean, Kamina groups or semi-extra special P groups give us something of which we can compute the commutativity, but we cannot somehow compute the commutativity. We cannot control the decomposition within central factors. I think I should stop here. Thank you very much.